Hello, everyone. In this lecture, we're going to continue the discussion of exponential family and generalized linear model. And in the last lecture, we talked about the exponential family. We showed that the exponential family follows the generic formula like this, and it covers a very wide range of distributions like the Gaussian distribution or the Bernoulli distribution. But if you just apply the exponential family, it's more like a statistics because you have a bunch of data samples, right? And then you fit a distribution on those data samples. You don't have a particular prediction task. And in machine learning, we usually care about prediction. And we have some features of some data samples. And we want to make a prediction, or either what is the price of the stock, or what is the category of the animal. Right. So in this lecture, we are going to extend the exponential family to the generalized linear model. Or known as GLM or GLIM. The basic idea is since the target is unknown during inference, and we would like to model the target in a probabilistic way, why not let's assume my target is some exponential family, okay? And that is very intuitive because exponential family, it covers many distributions. But in machine learning, the target is not the same for different samples. The target really depends on the feature of the data sample. So I would say, given that data sample X, my target would be an exponential family, okay? And obviously, I would say the parameters of my exponential family must be some function of X, okay? Some function of X. Right? Your input X, the feature of data, really affects the distribution of your target. And then you have a different prediction for different data samples, just like in linear regression. So this is my line. And then I have different, Gaussians, right? So this is X, this is T. And given this X, I have a Gaussian distribution like this. But given another X, I have another distribution. So the probability of T depends on the input. And given the input, the target is an exponential family where the parameter is a function of X. Okay, so this is the first development. Second, I would make my thing simpler. I would say it's a function of W transpose X. Okay, because we are considering the linear model, okay? It's a generalized linear model. So we assume that the exponential family, the parameter of the exponential family is a function of linear transformation of X. Is that fair? In this way, I can represent the generalized linear model in the following diagram. So I will say my X and W enters the model by inner product, okay? Because it's a linear model, my assumption is that my X enters the model by inner product with my weights W. And based on that, I have the Xi, okay? So this is the Xi, which is just the inner product of Wx. Then based on the Xi, I would transform it to my mean parameter, okay, mu, which is my mean parameter. Okay. That is the mean of your sufficient statistics. And oftentimes here, the sufficient statistics is just T. So I call this function F, response function. And based on mu, I mentioned that there's some correspondence between the mean parameter and the natural parameter. So this is the natural parameter. Okay. And this is called psi, okay, which is called the link function, psi. And based on my natural parameter, I define my exponential family for T, okay? So this is the development of a generalized linear model. Basically, it says my data enters the model by linear transformation, and then I have a response function mapped to the mean parameter. And further, I map it to the natural parameter, and eventually I define a conditional distribution on T as the exponential family. So usually we write the exponential family as eta here. So the eta is actually the psi, the link function of my response function of my W transpose X. Okay. And in machine learning, we typically care about the prediction, right? Is often the expectation of T, right? So in the Gaussian case, we predict what is the most probable value, what is the expected value, because the Gaussian is symmetric, the most probable value is just the expectation. And in the Bernoulli case, you consider the chance that the target is 1, or in the multinomial case, the softmax regression, you care about the chance that the target is indeed for this category, right? It's also the expectation. So in most machine learning models, it's the prediction is just T, expectation of T given X. Okay, so this is the generalized linear model. And it appears that there's some complications saying I first map it to mean parameter and then I map it to natural parameter. So why not let's just combine them together? And I would like to choose f equals inverse of phi. So I try to cancel them out. Okay, that simplifies things, right? So I would say, why not let's choose f equals psi inverse. Then my model is T given X is the exponential family of W transpose X. Okay. If that happens, we call it canonical response. Canonical response. And this is the most widely used assumption in generalized linear model. By default, we just have the canonical response. You don't have to go to the mean parameter and then get the natural parameter. You directly get the natural parameter by the psi. Okay. And then the prediction is oftentimes about the mean parameter. So you need to compute the inverse of the psi as your f. Okay. If you go in this way, it's the f inverse, which is chosen as psi. Okay. And this is chosen as psi inverse. Okay. So this is the canonical response. If you have the canonical response, I can simplify the diagram as saying I first have X and W. I have a linear transformation. Okay, it's the psi W transpose X. My psi is directly eta. Okay, psi is just eta because you first transform it to mu, then you transform it back. It's just eta. Okay, and based on my eta, I can just define my exponential family of T. Okay. But my prediction is oftentimes about the mean parameter. So I would compute the mu parameter, the mean parameter by my psi inverse. Okay. So this is the generalized linear model with a canonical response. Example. The Gaussian case. We assume that my target is sampled from my Gaussian distribution where the mean is the W transpose X, where the variance is sigma squared. Okay, this is my model assumption. And then the variance is a constant, right? You remember in the linear regression model, we don't have the assumption for the variance. We assume the variance is already there, but the true model itself is the linear or the affine transformation, right? So, so this is the mean parameterization, but we can follow the natural parameterization as saying I first have x and w, okay, and then I get the psi, which is my eta, okay. Then I would like to directly compute the mean, okay. The mu is, psi inverse, okay. So the mu is psi inverse. Then we remember in the last lecture, we talked about that there's some correspondence between the mean parameter and the natural parameter, and it's here, right? So I would say mu is sigma square eta 1, right? So mu is sigma square eta 1. So I would say mu is sigma square eta 1, okay? Eta 1 is just this eta, okay? Then sigma square is a constant. Why not let's absorb my sigma square into my w, okay? It doesn't change anything. So in this case, I can set my f, the response function for Gaussian, as the identity. All right, is that clear? So you have the feature x inner product with your weights, and then you get the psi, which is also your natural parameter. And theoretically, you should multiply it with the variance, but you can absorb the variance into your weights. So I would say the expectation of my target given some data input is just the W transpose X. I can absorb the unknown variance into my weights. Okay. So in this case, the expectation of my T given X is just the W transpose X. So this is the Gaussian case. Another example is the Bernoulli case. In the Bernoulli case, still I have the X and W, and I enter into my model as the inner product. It gives my psi, which is also my eta, okay? Then I would like to compute the mu. The mu is actually, again, the psi inverse of my eta, okay? But this time the psi inverse is here, okay? It's here. So I guess I've erased that, but I think I mentioned that here. So I can compute it again. So I would say the log of pi divided by 1 over pi is my eta. So pi divided by 1 over pi is the exponential of eta. So 1 over pi divided by pi is the exponential of minus eta. And then, okay, pi is the 1 divided by 1 plus exponential of minus eta, which is the sigmoid function of eta, okay? So that pi is just the mu, okay? It's just the mean parameter. It's the sigmoid function of eta, okay? So that's why in logistic regression, we assume that my model comes into my data by linear transformation. We call it Z, but you can also call it psi, or you call it either, it doesn't matter, okay? Then I will say my prediction Y, which is actually the expectation of your target being 1, okay, given X, right? It's just a Y. Is just the mu here is just sigmoid of eta, okay? It's 1 plus exponential to the minus eta, okay? And this precisely tells you how the sigmoid function arises. So the sigmoid function arises with the assumption of generalized linear model plus canonical response. Okay, then it gives me the sigmoid function. Okay, of course, for Bernoulli case. And for the categorical case, you get the softmax regression, okay? So now the question is the canonical response. Is that necessary? Okay. Or can we design other response function? Yes. I think I mentioned the probit response function. That's also doable, especially if in some cases, especially like you have a Gaussian prior, you have the sigmoid likelihood. It doesn't give you a very good distribution. But what if you have the the CDF of a normal, then it gives you some normal distribution. Okay. But if you use the canonical response, I would have a very nice probability for you. I would say the partial derivative of my log likelihood, okay, the log likelihood for a data sample M with respect to my W has the same form, which is it's y minus t. Okay, something like this. Okay, so you remember in both the linear regression or in the logistic regression, you both have this formula. And the precise reason is that you use the canonical response for the generalized linear model. Then without deriving it for every single model, you all get this. And the reason is that we can derive this property for the whole family. Okay. So I will say the probability of my target for a particular data sample M, where I omit M for a particular data sample X, okay? I just omit the superscript M, it's omitted. I assume it's an exponential family, right? You see it's my assumption, it's the exponential family here. So I would say it's the h of x. Exponential either of x, right? Either times sufficient statistics. Okay, sorry. It's h of t because my random variable now is t, okay? Then exponential of my either times sufficient statistics. And this time my either is W transpose X because I use the canonical response function. W transpose X times sufficient statistics. And I assume my sufficient statistics is just T because in most cases, I care about the prediction as my expectation of the target times my sufficient statistics, which is T of T, okay, minus A either. Okay. So this is the probability, or this is the likelihood. Then my J, is the log of my probability, P T, I also omit M, which is the, if I take the log here, then log of H goes to a constant term, and then the log and exponential cancels out. So I would say W transpose X times T of X, sorry, T of T. Minus A either plus some constant term, okay? The constant term should be log H of T, but it doesn't matter. So now I will compute the partial derivative of J with respect to W, okay? So this is the inner product. So you can think of this as a vector because T of T is just a constant, okay? So for this term, it just gives me T of T times X. Okay, and for this term, minus, okay. So now I would like to take the partial derivative of J with respect to my W. For the first term, I take the partial derivative with respect to W, it gives me that term, okay? Because X is a vector and T of T is a scalar. We assume we only have one sufficient statistics, which is the mean of your target. If you have multiple sufficient statistics, the W now becomes the weight matrix, okay? that complicates things a little bit, but now let's assume a simpler case. Okay, so x is a vector, t is a scalar, minus, okay, we know the partial derivative of a either with respect to either, I know that. And it's possible that I compute the partial derivative of my either with respect to w, okay. And also, to simplify things, I assume the either is a scalar, because if it's a vector, then you need to be careful. It may be a matrix multiplication, and you need to implicitly sum over the effect of a either on w through different either's, okay? So if we have the scalar either, then it's simpler, so we deal with this. What is that? That is the moment generating property, right? The partial derivative of a either with respect to either is the first order raw moment, which is mu. Okay. Okay. And this mu should be a scalar. And what is that? So either is, W transpose X. So this term becomes so this term becomes X, right? So either is here, either is W transpose X. Then I take the partial derivative with respect to W, then I get X. So now I can say this is the T of T minus mu times X, okay? And the T of T is my data sample, right? And oftentimes the sufficient statistics is just the target itself. And minus mu, the mu is the mean parameter of your exponential family, which is just your prediction. So it's y of n, okay? X. And you get it, okay? X is a vector. So this tells you that if you use the generalized linear model with a canonical response function, then the partial derivative of your J with respect to your weights. Where is your weight? Weight is how your X enters your model, okay? It's the inner product of your weight. It gives you the target minus the prediction times X. And the trick here is the loss should be the negative log likelihood, okay? The negative of this term, okay? Then it's the same as what we have seen, okay? So this almost finishes our discussion of the generalized linear model. I decided to include another topic for this lecture, which is an application for exponential family. In particular, we're going to talk about the Markov network, or the Markov random field. So this is a very classic topic in probabilistic graphical models, but we're not going to talk about probabilistic graphical models in general or in a systematic way, but we're just going to apply the Markov network or develop the Markov network for a particular task and apply the knowledge we have learned for exponential family to solve that task. Okay, so the task we're talking about is maybe social network analysis. Okay. And in particular, we're going to do, for example, political polarity classification. So the basic idea is in social networks, people are connected. So each node represents a person, And then an edge shows that they are connected in some social network, maybe Twitter follow or followed by, or maybe some mutual friends. So we don't mind whether it's we think of it as an undirected graph, okay? So there are different graphs. Okay, this is a snippet of the social network, and we have some other snippet of the social network, maybe like this. Okay. Something like this, okay. So this is another snippet of the social network. And there are even more snippets. You can think of each of the snippet is a data sample, right? And we know that people have different political polarities. For example, some people support the Democratic Party, some people support the Republican Party. So we think of, let's simplify the things, we think of only two parties, okay? One is party 1, and the other is party 0, okay? So each person supports either 0 or 1, or and each person must support one party. So this is my assumption or simplified assumption, okay? Then we have a node for the label. For example, this is 0, 0, 0, 1, 0, 1, 1, 1, 0, okay? And this is maybe 1, 1, 1, 1, 0, or maybe 0, 1, 0, 0, okay? And this is 0, 0, 0, or maybe 1, 1, 0, 0, 1, 0, okay? Something like this. Okay. So each node is labeled by its target, or it can be either 1 or either 0, but it must be 1 or 0, meaning that the person either supports one party or the other party. Okay. So the training data looks like this. Okay, you can think of it as a supervised learning task where the input is the structure and the output is the political polarity, okay, of a node. So these are the training samples, and each snippet is one data sample. And the inference, okay, is I have a new snippet, okay? Maybe I go to a different community and people are connected in a different way. Maybe something like this, okay? And I happen to know that, for example, some of them, this is 0 and this is also 0, okay? These two people support the 0th party, and these two people support the first party, okay, party 1. So the question now becomes, what is the political polarity of the remaining nodes, okay? So it's a little bit different from our traditional supervised learning, where in the prediction, it's not about the feature, but it's rather a part of the labels. But the goal of prediction is to predict the remaining labels, okay? And obviously, this task cannot be easily solved by linear regression or logistic regression. There's some subtlety between different nodes, okay? You see, if two people are connected, they are friends, then it's more likely that they have the same political polarity. But it's not a necessary condition. They may have different political polarities, right? But it's more likely that they both have 1 or they both have 0, okay? And maybe I have some other features saying, okay, I know more people are supporting the Democratic Party, so more people are being 1, okay? It's a little bit biased towards 1, okay? So these are the intuitions, and they can actually be learned from the training data, okay? So you can count how many people are 1 or how many people are 0. You know the bias, and you know the affinity between two connected people, okay? So how can I address this problem? So this shows the beauty of a principled approach. By saying a principled approach, I mean that we have a framework to solve different problems. All the problems look different, but I have the same thing, and then I can apply the same criteria, and I only need to solve the small components of the principled framework, okay? So what I plan to do is I plan to do maximum level estimation. So I plan to define a probability distribution over the labels, the possible label assignments, okay, given the graph. Okay, notice that the probability distribution is not saying, okay, what is the chance of having this snippet instead of that snippet? No, the probability distribution is saying, given this snippet, what is the chance of having label 0, 0, 0, 0, 1, 1, 1, 1, 0, instead of 1, 1, 0, 1, 0, so on and so forth. Okay, so if you consider all kinds of label assignments, then the sum of these probabilities will be 1. Okay, it's not the probability of different graphs they sum to 1. Then I can do maximum level estimation. Okay. Then, given the task, I can do the max a posteriori inference. So I can say, so this is the model, this is the training, and this is the inference. When prediction, I say my y, p of y, maybe I call it y1, y2, y3, y4, y5, y6, 7, given y8, y9, y10, and y11, okay? So I would predict the probability y1 up to y10 will be the argmax of p of y1 up to y10 given all the other things, okay? y8 up to y11, okay? So this is the general idea, because we do max a posteriori inference. We don't deny what we have observed, but based on my observation, I will pick the category that is most likely, okay? So this is my plan. So how can I do the model a probability distribution over the labels over a graph? So what I suggest is exponential family. So I will suggest exponential family. Okay. So I can write it here. So exponential family says P of these y's, okay, I can call it y. So suppose I have n nodes, y1 up to yn, okay. The probability of these nodes, given some parameters, is the exponential of the, exponential family is h of y given either transpose t of y minus a either, okay. And I would set h of y equals 1. So this is my design choice. I don't have to say what is more likely for y. Then the sufficient statistics, as I mentioned, is just the features, right? So given these label assignments, what can we say about this label assignment? Okay, what are the features? And A either is the normalization term. So you can think of it as, I can write the normalization term out. It's the exponential of either transpose sufficient statistics of y of my labels, okay, which is just the features of my labels. Okay, so now the questions are, what are the features? Okay. So the intuition is, first, you have the bias. Okay, maybe more people are supporting party 1 instead of party 0. Second, people have an edge. It's likely to have the same polarity. Okay. So I would say my feature f of y include, okay, y1 equals 1, y1 equals 0, okay? Right? And y2 equals 0, okay? 1, y2 equals 0, something like this, okay? So on and so forth. So I would say whether my first node is 0 or whether my first node is 1, and then my second node 0 or 1, 0 or 1, until the nth node is 0 and 1. Okay. So this is my first set of feature, which is the singleton feature. So I can say f of node I, okay. It can choose either 0 or 1, and say whether my node I is 1, okay, is the node I equals 1, okay, or yi equals 1. And I have another feature, 0, which is this. Okay. So this is my first set of features. Suppose you have n nodes, then you have 2 n features here. Okay. The second set of features is the pairwise features, because we mentioned that two people connected are more likely to have the same polarity. Okay. Then I would say here for I is 1 up to n. Okay, suppose we have n nodes in total. Then the second set of features is f of ij, okay, being 0 and 0 is whether y1, yi is 0 and yj is 0, okay. Fij is 0, 1, saying whether my yi is 1 and yj is 1, okay. So I have 4 features for each edge, okay. 1, 0 is whether my yi is 1 and yj is 0. And 1, 1 is whether my yi is 1 and yj is also 1, okay. So you see, here for ij being an edge of the graph, okay. So I'm learning whether you have the, for whether a node would be more likely to be 1 or the node more likely to be 0, okay. And I'm also learning the pairwise features, whether it's more likely to be 0 and 0 or 0, 1 or 1, 0 or 1, 1, okay. So now I have that many features. Then I can plug in all these features into here. But the issue is that, you have many features. And for different data snippets, you have different n, okay? And this node, for example, the first node here is different from the second node there, right? So you must share the either for different nodes, right? So the either is the weight of the feature, but this feature may indicate different nodes, but I share the same either for you, okay? So in this way, I would suggest the probability is the exponential of okay. So I have the singleton feature, which is the either 1, okay, and either 0, okay. So I have n nodes. Then for each of the nodes, okay, either 1, okay, right. So if a node has feature being 1, then how much it contributes to the distribution is given by exponential of either 1, right? So this is the pointwise features. And I have the pairwise features, which is the ij in my edge, okay? So suppose I have an edge set, then for any pair ij, Then I have here I say my features are either 0, 0, either 0, 1, either J1, 1, 0, and either 1, 1, okay? Then it should be either 0, 0, Fij, 0, 0, plus. So here is times, okay? Either 0, 1 times f of ij 0, 1. So I have 4 terms. Okay, done. So based on the exponential family, we can very intuitively define the probability distribution over all different label assignments given a graph as the exponential of the linear transformation of your features. And the features include both pointwise features and the pairwise features. And for pointwise features, it says how likely a node takes value 1 and how likely a node takes a value of 0. And for pairwise features, it tells you how likely that the node is 0, 0. I mean, a pair is 0, 0. How likely is a pair of 0, 1? How likely it's 1, 0? And how likely it's 1, 1, okay? So in this way, I just define the exponential family on this graph. So model is done. In training, so, you know, the parameters are actually either zeros or either 1, either 0, 0, either 0, 1, either 1, 0, either 1, 1. Okay, anyway, there are many parameters, but in general, I can say my probability distribution is the either transpose some feature of y, okay, minus a either, or I can say it's 1 over c here. Okay. Then I can do the gradient-based learning for either, and I can take the partial derivative of the log likelihood with respect to either, the log likelihood. Okay. What is that? I don't have to compute. I know this is the expectation of Fy in data. Minus the expectation of f of y in model. Okay. Or maybe it's the negative log likelihood. So now I need to cheat a little bit. I need to refer to my previous derivation, whether it's plus or minus, okay? So let's see. Okay. Okay. Here it says, this is the expectation in data. So the log likelihood. So the derivative for log likelihood is the expectation in data minus the expectation in model. Okay, expectation in data minus the expectation in model, okay? So we just count how likely it is in your data and we match it with the model expectation, okay? But what we are not going to discuss is how can I compute the model expectation? That is not a very easy thing. Or what you can do, I mean, a brute force approach is you can enumerate all the assignments and you compute the unnormalized measure, and then you normalize it by all the terms of your enumeration. And that doesn't seem to be a fancy approach because you have exponentially growing number of terms. So in this way, you can do all kinds of approximations like a sampling-based approach. You try a Monte Carlo sampling and you get an estimate, or you can do other variational stuff. That's beyond the scope of this course. But in this example, we show that the exponential family is indeed a very general family of distributions. And with the philosophy of the exponential family, I can define some probability distributions over the assignment, label assignment of the graphs. And then I can do the learning, or it just directly gives me the equation. If you seek for a closed form solution, you set it to 0, and it gives you the moment matching. But usually we don't have the closed form solution, so you do the gradient-based approach by this. Okay, that's it for this video. Hope you have fun in the exponential family and generalized linear models. See you next time.